All right, so this should be a video for 11.2, and so we're going to talk a little bit about the properties of exponents and logarithms. We're also going to be talking about derivatives and some of the stuff that happens with these particular functions. So let's get started. So we have f of x equals e to the x for our first case. Anytime that we're taking the derivative of the exponential function, we're going to get back out the exponential function from it. So we have our f prime of x equal to e to the x. This holds true unless we have a different base other than e for our function. And we'll see that coming up in the h of x function. But first, let's look at g of x equals ln of x. So for g of x equals ln of x, when we take the derivative of that function, with the natural log function, we're going to get g prime of x equals 1 over x. And this looks a little bit weird. It's somewhat interesting to kind of think about, but the actual derivative here comes out as taking whatever's inside of that ln function and putting it in the denominator and ending up with what that would be overall. So that's an interesting kind of relation that we have there. Let's go ahead and look at h prime now, the one that I alluded to earlier. H of x equals some base to the x power. When we take the derivative of it, would be h prime of x equals ln of that base b times that base b to the x power. So we get basically out the same b to some power, whatever x you've got, that we end up with when we're plugging it in. And we're multiplying it by that ln of b, so ln of the base. So that's just a little coefficient that gets thrown in front of our exponential. Even though the exponential has a different base, it's still increasing exponentially or decreasing exponentially, whichever way it's ending up. And so we have that for our relation for just a general exponential. If we're interested in a general log function, so log base b of x, we can set it equal to this k of x function here. And if we take the derivative, we're going to end up with k prime of x. And that's going to equal our 1 over ln of b times 1 over x. And it's interesting because that ln of b comes back up again in this relation. And we have, again, this 1 over x that comes up similar to our g prime of x. And we'll end up with this as a complete relation for what the derivative would be. So it's an interesting kind of way that it ends up here for this particular one, where we start with log base b of x and take the derivative to get 1 over ln of b times 1 over x. So that's what that'll be for these 4 forms of the function, or 4 different functions. And if you ever run into one of them and need to know the derivative, you can basically use these to figure out what it's going to need to be. All right, so let's continue on. I just have a slide here to give you a couple of examples of ways that you can kind of work with logarithms. Anytime that you have a log of any base, all of these will hold true. I just didn't include a specific base for some of these first ones, so don't worry too much about what the base of these are. It could be a base E, it could be a base 10, it could be a base 2, whatever you want, as long as the base is a valid base. And I think the only base that doesn't work is 0 and 1. I think those are the only 2 that don't. I think all the others do. I think just some of them might look a little weird. So if you are messing around with it, you can test how the functions work on the calculator and see where they end up and stuff. But I think the only ones that don't are 0 and 1. All right, so if we're looking at this, log of a and b, a times b equals log of a plus log of b. So the way that you can think of this is the log function basically looks at what the potential exponent of the base would need to be in order to equal this interior value. So if we're looking at what that exponent of the base needs to be in order to equal these, then we've got the potential to break up two numbers that are multiplied together into two separate entities and look at each of them individually and get what their exponents would be and then add them together at the end. And so that's why this kind of works, this first part here. And then we can do the same thing with a over b. So if we were doing a fraction where it's a over b, we could end up with log of a minus log of b for that equal to log of a over b kind of equation. And this works for the same idea as the a times b, except for we have a over b now, which would be like a times b to the negative first power. And so you can think of it as if you're taking the exponent of what that a would need to be for whatever base, and you're dividing by b, whatever b's base would, or exponent would need to be for whatever base. And so if you had something of a particular exponent to a certain base, or a certain base to the first exponent for a, and then we're dividing by that same base to a certain exponent for b, it would be like you're subtracting whatever the exponent for b is from the exponent for the a number. And so you would end up with this relation where you have this log of a minus log of b situation coming up. And so it's all about thinking of the relation of what the log function kind of means as the inverse of its base's exponent. And I've kind of got that relation written down here, so you can kind of look at it and kind of think of it a little bit more. But that's how you can kind of interpret some of these simplifications. For this particular one, this is also talking a little bit about how the exponent of a number can sort of be pulled out of the log, where you can think of whatever the exponent is as sort of a constant that can be rolled out. And so this is another good relation to have on hand to kind of think about. We can also talk about specific values that'll come out. So log base b of b would equal 1 because the log base is the same as the value that we're looking at. So it's sort of like you're saying b to the first exponent is going to equal 1 because that exponent is 1 of whatever the base we're looking at. Similarly, if we had log base b of b to the nth power, that would be equal to n because it's taking whatever base b is to the nth, there are n of them inside of there. And if we were going to do the same properties as we had up here, we could just break it up into a bunch of log of b plus log of b plus log of b, just we would have n of them there. And that would end up as log base b, or that would end up as n times log base b of b, which is equal to n times 1, which is equal to n. And so there's a couple of relations there and a couple of ways that you can work it out to come up to that particular value. We can also talk about what happens if we do log base b of 1, where 1 is basically the base b to the 0th exponent. And so you can do that relation where you're saying it's to the 0th exponent, and that 0th exponent then implies that the value of log base b of 1 equals 0. And so that's how you can kind of think of what that one is and how that relation works. And so this is just a nice little talk about what logarithms kind of have for some relations. And this is hopefully going to help you in terms of looking at logarithms just in general to kind of see how they work and help you kind of get some intuition on figuring out problems relating to them, both in this class and beyond.